Hello, everybody. Today I'm going to talk about an article that's called Development of a Pancreas-Liver Organ-on-Chip Coculture Model for Organ-to-Organ Interaction Studies. Type 2 diabetes mellitus is the most common form of diabetes, representing 90% of the diabetic patients. It is caused by the insensitivity of target tissues to insulin and impaired insulin secretion. This disease involves interactions between several organs, including the pancreas, liver, muscle, adipose tissues, kidneys, and gut. Also, it triggers an insulin resistance state characterized by a drop-down of glucose uptake. This state of hyperglycemia triggers the increasing insulin secretion, followed by hyperinsulinemia and beta cell proliferation as a compensatory effect for the insulin resistance state. Pancreas fails to adapt to the increased blood glucose level. To study these interactions between organs, animals models have failed to faithfully reproduce the human condition and lose relevance when extrapolating the results to humans. In vitro cell cultures are mainly performed in static 2D cultures using conventional multi-well plates, which do not accurately reflect the physiological in vivo microenvironment. Also, tissue engineering 3D culture has been used in the form of spheroids culture in 3D hydrogel and organoid, dynamic organ-on-chip culture, and coculture models were used also in order to provide a more appropriate microenvironment for tissue maintenance and development. In this case, the microfluidic organ-on-chip culture improves the exchange and transports of nutrients, oxygen, metabolic waste, hormones, and other chemical, and creates physiological-like situations such as the liver zonation, shear stress, and chemical gradients. Cultures of two or more organs in separated microbioreactors or microchips and connected by soluble factors exchange through the microfluidic network. Potential of this technology for liver and pancreas interactions via the insulin glucose regulation is studied in this article. Also, the objective with this article, with this approach, is to study the hepatic disturbance by removing the insulin from the culture medium. The restoration of hepatic function thanks to interaction between the liver and endocrine pancreas through the circulating hormones and factors in the coculture configuration. For this, the authors used 4 different chips that we're going to talk about later. Now we're going to deal with the device design and fabrication. In this article, the author decided to use 2 different biochips, one for the liver and one for the pancreas. These chips were connected serially. The pancreas-on-chip model is observed here. It consists of a microstructured bottom layer used to trap isotopes of Langerhans, and it was composed of 600 microwells. It is located here, and we can see this from the inside of the chip. 600 microwells measuring 400 milliliters in diameter with a depth of 300 micrometers and spaced by 50 micrometers. It has a second PDMs layer, that it's the top layer, with a reservoir, and this, here is the top layer. It has a depth of 100 micrometers. A microchannels network placed at the inlet and outlet of each layer made it possible to distribute the culture medium homogeneously in the biochip. This is the microchannels network that allows us for an homogeneous distribution of the culture medium. The liver chip has the same has similar design. It consists of a microstructural bottom layer. You can see the bottom layer here. It consists of a microstructural bottom layer composed of microchannels and microchambers. Here is the microchannels and the microchambers of the liver on chip model. These chambers measure 1.2 centimeters in length, and it's observed here. All of the system, the channels with the chamber, 1.2 centimeters in length, 1 centimeter in width, and 100 micrometers in height. Second PDM layer that's similar for both of the organs on chip, of both of the organs. The second PDM layer is a reservoir, acts as a reservoir with a depth of 100 micrometers, and the microchannels network was also present in the inlet and outlet to ensure homogeneous culture medium distribution. These PDMS biochips were manufactured using a optical molding process. PDMS was cured for 2 hours at 75 degrees Celsius degrees, and the surfaces of the PDMS layers obtained were activated with reactive air plasma and brought together immediately to form an irreversible seal. The experimental setup designed by the authors for the culture in the biochip was composed of a perfusion loop. This named here as dynamic liver biochip is what it's called also the perfusion loop. It is composed by the culture medium tank that acts as a bubble trap, a peristaltic pump, and 1 or 2 biochips. It depends on the approach that we are using. There, the peristaltic pump, the biochips, and the medium tank were connected using 0.65 millimeters interior diameter silicone or Teflon tubing. For this study, 4 groups of biochips were investigated and compared. 1, the hepatocytes biochip monoculture with insulin, that it's called as liver monoculture ITS plus. The hepatocytes biochip monoculture without insulin, that is called or is known as hepatocytes or liver monoculture ITS minus. Pancreatic, it's observed here. Pancreatic islets biochip monoculture, only islets, and the liver pancreas coculture that it's as hepatocytes and islets of Langerhans without insulin. Here we have a closer look of the setup used for the dynamic culture in biochip. Here, the hepatocytes chip or islet chips here is connected to a peristaltic pump and to the reservoir, to the culture medium reservoir, which acts as a bubble trap. This is used for the monocultures, either for hepatocytes or for islets of Langerhans. For the hepatocytes islets culture, the setup is the same. There is only one difference, that is the hepatocytes and islets chip are connected serially. For the pancreatic islets culture in the biochip that is observed here, the pancreas and chip, the biochips were previously filled with culture media in order to remove the air bubbles and moisturize the circuits. Preconditioning process was carried out at 1 hour at 37 Celsius degrees in the incubator. Pancreatic islets in the preservation solution were washed with cold culture media and gently diluted. To minimize islets damage, wide orifice pipette tips with low binding were used. Islets were counted in biochip to keep a record of approximately 40 islets per biochip. Circuit was then connected to the peristaltic pump and the perfusion started. They were continuously incubated at 37 Celsius degrees in a 5% CO2 supplied incubator. For the hepatocytes biochip cultures, they are observed here, biochips were coated with rat tail type 1 collagen and incubated at 37 Celsius degrees in an atmosphere supplied with 5% CO2 for 1 hour. After that, it was washed with seeding medium and the freshly isolated hepatocytes. The hepatocytes population was about 5 10 to the 5th cells per biochip. These number of cells were loaded into the device. To keep the seeding medium inside the culture chamber during the load, Biochip inlet ports were closed using two syringes containing 500 microliters of seeding medium, and the biochips were placed in an incubator at 37 Celsius degrees and 5% CO2. After 24 hours, seeding medium was replaced by the culture medium, and the biochip integrated into the perfusion experimental setup to launch the dynamic culture. The difference between the pancreatic biochip and the hepatocytes biochip is that the hepatocytes biochip culture requires a pre-process that consists in the injection of collagen to ensure that the cells will bind to the bottom of the chip, and the use of the seeding medium. Preparation of the chip is different before the load of the hepatic. For the hepatocytes islets coculture that is observed here, the liver and pancreas biochips were prepared separately, as I mentioned before. First, the hepatocytes were inoculated in the liver biochip for 24 hours of addition and 24 hours of perfusion. The process is observed here. Day 0, the liver biochip is prepared and the hepatocytes were loaded. At day 1, there is a medium exchange. It's what I mentioned before, the 24 hours of perfusion. And the medium is sampled. At day 2, after the 24 hours of addition, 24 hours of perfusion, the pancreatic islets biochip were prepared. After 1 hour at rest and islet sedimentation, the liver's perfusions were stopped, and one pancreas biochip and one liver biochip were serially connected to each other to create a pancreas-liver coculture model. The culture medium for the culture condition was 1-1 mixture of pancreatic islets, RPMI, and hepatocytes Williams D. MIDI, including ITS from the last one. For the coculture, there's no insulin added to the culture medium, only the mixture of the pancreatic islets media and the hepatocytes medium. For the pancreatic islets, the medium is RPMI 1640, and for the hepatocytes, it is Williams D. Using this approach, this study, they proposed a new liver-pancreas interaction model in biochips to investigate the crosstalk between the organs. They compare different markers, different genes, different differentiation markers to ensure that there is a crosstalk using this approach. The characteristic functions of the hepatocytes and islets coculture model were evaluated using these approaches. The hepatocyte monoculture without insulin led to modulation of both glucose homeostasis targets and hepatic differentiation markers. The coculture with pancreatic cells producing insulin helped recover the hepatic function, illustrating the benefits of the two-organ model. The presence of the hepatocyte in the coculture model helped modify the islet's response via the increase in insulin secretion and the modification of the expression of the gene involved in insulin glucagon homeostasis. The pancreas-liver organ-on-chip model could reproduce several physiological responses and demonstrated the potential of our approach to reproduce and investigate complex in vivo patterns using alternative in vitro methods.